This presentation introduces key concepts of urban density and risk mitigation. It examines different density topologies, measurement techniques, and planning approaches used to reduce risk in dense urban environments. The lecture also addresses social dimensions of density and risk, reviews analytical tools and methods, and concludes with emerging trends shaping resilient urban development. By the end of this lecture, students will gain an understanding of how urban density shapes both risk and resilience in high-density cities. The lecture will introduce key planning and design strategies used to reduce risk in compact urban environments, with a focus on public space, infrastructure, and green systems as essential components of urban safety. Students will also explore the social dimensions of density, including vulnerability, service accessibility, and community resilience. Overall, the lecture aims to demonstrate that urban density is not only a source of risk, but can be intentionally shaped as a tool to support safer, more resilient, and more sustainable urban development. Density refers to the concentration of physical or social elements, such as people, buildings, or activities, within a specific geographic area. Urban density is a more complex, multi-layered concept that reflects how built form, population, land use, and infrastructure overlap in cities. Urban density describes how people, buildings, and land uses are concentrated in a city, shaping spatial patterns, infrastructure performance, and environmental conditions. Compactness refers to the spatial efficiency and closeness of urban development, including building proximity, reduced sprawl, and mixed-use form. Compactness is the degree to which urban development is spatially concentrated, minimizing sprawl while maximizing proximity and efficiency. Exposure refers to the presence of people, buildings, infrastructure, and economic activities in areas that may be affected by hazards. Vulnerability is the sensitivity or susceptibility of people or systems to damage during a hazardous event. It includes physical, social, economic, and infrastructural dimensions. Risk is the likelihood of harmful consequences resulting from the interaction of hazards with exposed and vulnerable urban elements. Risk mitigation is the process of reducing hazard impacts by lowering exposure and vulnerability through planning, design, and policy measures. Urban density can take different forms depending on how buildings, land uses, and people are arranged in space. Understanding these topologies helps us analyze how density affects mobility, exposure, resilience, and overall urban performance. In this section, we examine the main forms of density found in cities around the world. Horizontal and vertical density describe two different ways that cities become compact. Horizontal density develops when buildings spread out across a large area but remain relatively low rise. This pattern often produces continuous built fabric with limited open space. Streets tend to be narrow, and land coverage is high. Although movement distances remain short, horizontal density can reduce ventilation, increase heat accumulation, and create challenges for emergency access. Vertical density concentrates development upward through multi-story or high-rise buildings. This form allows more open space at ground level and can support transit-oriented development. At the same time, it introduces new challenges such as pressure on elevators, vertical evacuation difficulties, and greater reliance on structural safety during hazards like earthquakes. In practice, most cities combine both forms, but the balance between them significantly shapes resilience, energy performance, and livability. Mixed-use compact development brings residential, commercial, institutional, and recreational functions together within a walkable area. By placing daily activities close to each other, this model reduces travel distances, supports public transportation, and creates vibrant street life. From a resilience perspective, mixed-use density offers several advantages. It distributes activity throughout the day, creating natural surveillance and social cohesion. It reduces dependence on long-distance mobility, which can fail during emergencies. It supports multifunctional infrastructure, such as shared public spaces and integrated green networks. However, if mixed-use areas lack adequate open space or evacuation routes, the concentration of people can produce severe congestion during crises. Therefore, successful mixed-use environments require careful planning of mobility corridors, open spaces, and building codes. Informal settlements represent one of the most intense forms of unplanned density. They typically develop without formal regulations, infrastructure, or hazard-sensitive planning. Buildings are often constructed incrementally, using locally available materials, and streets evolve organically rather than through a planned network. As a result, these areas may experience extremely high person-per-hectare ratios, limited emergency access, narrow, irregular street patterns, aging or substandard structures, insufficient sanitation, drainage, and open space, high exposure to floods, landslides, fires, and seismic risk. Despite these challenges, informal settlements also demonstrate strong community ties and adaptive capacities. Understanding these dynamics is essential for upgrading programs and resilience-oriented interventions. Density can be measured using a variety of quantitative indicators. Common metrics include population density, people per hectare or square kilometer; building density, number of structures per unit area; floor area ratio, FAR, total floor area divided by plot area; building coverage ratio, BCR, share of land occupied by building footprints; parcel density, number of land parcels within a given area; vertical density measures, total building heights or volumetric density. Contemporary studies frequently use GIS, geographic information systems, and remote sensing to measure density patterns across large areas. GIS enables mapping of building footprints, land use, street networks, and hazard zones. Remote sensing provides satellite-derived data on impervious surfaces, vegetation cover, and thermal characteristics. These tools allow planners to identify density hotspots, evaluate ecological impacts, such as heat islands, analyze evacuation networks, combine density metrics with vulnerability indicators, support evidence-based risk mitigation strategies. Urban planning plays a central role in reducing the risks that emerge in high-density environments. As cities grow, planners must find ways to create compact, efficient, and sustainable urban forms while also ensuring safety, accessibility, and resilience. This section focuses on key planning strategies that help cities manage hazards and protect communities. When we talk about urban compactness, we usually think of efficiency, shorter travel distances, more walkable streets, and better use of land and public transport. However, compactness also brings challenges. If it is not managed carefully, dense urban forms can increase exposure to hazards, overload infrastructure, and reduce emergency accessibility. So, the key question is, how can we design cities that are compact, but also safe and resilient? Let's think of compactness as a tool. When used wisely, it supports sustainability and livability. But without proper planning, it can become a source of risk. For instance, very tight street networks can delay evacuation during earthquakes or floods, while a lack of open spaces can limit emergency shelter areas. To balance density and resilience, urban planners and designers should consider a few principles. Encourage vertical growth rather than uncontrolled horizontal sprawl. Vertical development uses land efficiently and helps protect open natural areas. Include sufficient open spaces in dense districts, not only for recreation but also as refuge areas during disasters. Maintain connected and accessible street networks, allowing emergency vehicles and people to move safely during crises. Integrate infrastructure capacity planning with population growth, ensuring water, electricity, and transport systems can handle density safely. The goal is not to avoid density, but to shape it intelligently, so that compact urban areas remain safe, adaptable, and resilient under hazard conditions. A well-planned compact city should balance high efficiency with strong protection for its residents and systems. Land use planning and zoning are key tools for managing urban growth and reducing disaster risk. Land use planning defines where different activities such as housing, industry, and open spaces should be located, while zoning regulates how land can be used. including building density and height. When combined with hazard data, these tools help cities grow in a safer and more sustainable way. Risk-sensitive zoning avoids dense development in high-risk areas. Mixed-use zoning supports accessibility while maintaining safety. Buffer zones reduce exposure to natural hazards, and transit-oriented development concentrates density in well-connected and safer locations. Overall, effective zoning aligns land use with local risk conditions, protecting vulnerable functions and strengthening long-term urban resilience. Public spaces and street networks are essential components of resilience. They act not only as social and recreational areas but also as critical safety infrastructure during emergencies. Elements of a resilient public space network include connected open spaces, parks, plazas, and wide boulevards that can serve as evacuation or assembly areas. Clear evacuation routes. Well-marked streets and pathways leading to safe zones. Redundancy. Multiple alternative routes to avoid congestion and bottlenecks. Pedestrian-friendly design, ensuring that people can evacuate quickly even without vehicles. In dense districts, these networks are especially important because they compensate for limited private open space and high crowding. Green infrastructure plays a dual role in dense cities by enhancing environmental quality and reducing hazard impacts. Nature-based solutions help cities manage heat, water, and environmental stress more effectively. Key applications include urban forests and street trees to reduce heat island intensity, green roofs and green walls to increase insulation, reduce runoff, and support biodiversity, permeable surfaces for improved stormwater management, riparian buffers and restored wetlands to reduce flood risks, urban ecological corridors that connect parks and help cool dense areas. By integrating nature into the urban fabric, planners create healthier, more adaptable, and more climate-resilient environments. Building performance is a critical dimension of urban resilience. Strong building codes ensure that new construction can withstand earthquakes, floods, storms, and fires. However, many dense areas contain older structures that were built before modern standards, making retrofitting essential. Risk-reducing measures include enforcing updated building codes for all new development, seismic retrofitting of older or unreinforced masonry buildings, strengthening critical facilities such as hospitals, schools, and emergency centers. Fire safety upgrades including fire-resistant materials and improved evacuation staircases. Infrastructure modernization such as improved drainage or reinforced foundations. Investing in structural safety is one of the most effective long-term strategies for reducing casualties and damage during disasters. Urban density is not only a physical condition, it also shapes how communities experience, respond to, and recover from disasters. Social inequalities, service accessibility, and community cohesion strongly influence vulnerability and resilience in dense environments. Socioeconomic vulnerability. Dense cities often contain sharp social and economic contrasts. Certain groups face higher risk because of low income and limited savings, overcrowded or insecure housing, poor access to services, healthcare, education, transport, higher dependency ratios, informal or unstable employment. These factors reduce people's ability to prepare, evacuate, or recover after a hazard, making vulnerability analysis essential for risk planning. Community resilience and social capital. Community resilience refers to the ability of residents to support one another during crises. Dense areas can strengthen resilience if social networks are strong. Public spaces support interaction. Trust and cooperation exist within the neighborhood. However, in areas with social tension or weak services, social capital may erode. Inclusive spaces and community participation help build stronger resilience. Migration, poverty, and informal settlements. Many dense districts grow through internal or international migration. Migrants often settle in informal or low-income areas where risks are higher. Key challenges include limited legal and service access, irregular street layouts, overcrowded housing, location in hazard-prone zones, slopes, floodplains. Despite these disadvantages, informal communities often show strong adaptive capacity and local knowledge. Resilience strategies must address inequalities while recognizing these strengths. Risk communication and public awareness. Effective communication is vital in dense cities because disasters affect large populations quickly. Good communication should use clear, accessible language, reach diverse social groups, combine digital and community-based channels, counter misinformation and build trust. Strong awareness improves emergency response and reduces casualties. Governance and institutional capacity. Resilient dense cities require strong, coordinated governance. Key elements include enforcement of building codes and land use regulations, evidence-based planning and transparent decision-making, clear institutional responsibilities, stable funding for resilience measures, community participation in policy processes. Weak governance leads to unsafe densification and poor emergency capacity. Strong institutions are therefore critical for long-term resilience. Understanding risk in dense urban environments requires reliable tools and analytical methods. These tools help planners, researchers, and decision-makers evaluate hazards, identify vulnerable populations, and design effective mitigation strategies. In this section, we review key analytical approaches used in contemporary urban resilience studies. Spatial analysis, GIS, remote sensing, multi-hazard mapping. Spatial analysis allows us to examine how risk varies across different locations in a city. GIS, Geographic Information Systems, is one of the most widely used tools. It helps map buildings, population density, infrastructure networks, hazard zones, and environmental conditions. With GIS, we can visualize how risks overlap, for example, where high-density districts coincide with floodplains or seismic faults. Remote sensing provides satellite or aerial imagery that can detect land use patterns, vegetation cover, surface temperature, and impervious surfaces. This is useful for identifying heat islands, flood-prone areas, or informal settlements. Multi-hazard mapping combines several hazard layers, such as earthquakes, floods, landslides, and heatwaves, to show cumulative risk. This helps cities prioritize areas that require urgent attention. Overall, spatial analysis makes complex urban systems visible and measurable. Risk assessment models, qualitative, quantitative, hybrid, risk assessment models help translate raw data into meaningful risk levels. Qualitative models use descriptive categories, expert judgment, and community knowledge. They are helpful when data is limited or when understanding perceptions and behaviors is essential. Quantitative models use numerical indicators and statistical methods. For example, they may calculate hazard probability, population exposure, building fragility, or economic losses. Hybrid models combine both qualitative and quantitative elements. They are widely used in urban resilience because they integrate technical data with local expertise. Together, these models support a more holistic understanding of risk and guide targeted mitigation actions. Scenario planning and predictive modeling help cities understand how future events and decisions may influence risk. By exploring multiple plausible scenarios rather than a single forecast, these tools support long-term planning in dense urban environments, where small changes can have significant impacts. Predictive models, such as climate, seismic, or evacuation simulations, are used to estimate potential consequences and guide infrastructure and adaptation strategies. In parallel, participatory methods involve local communities in risk assessment, ensuring that everyday experiences and local knowledge are included alongside technical data. Finally, evidence-based decision-making relies on integrating diverse data sources to prioritize actions, allocate resources effectively, and design interventions that meaningfully reduce urban risk. As cities become denser and face growing environmental and social pressures, new approaches are shaping the future of urban resilience. These emerging trends reflect advances in climate science, urban design, digital technologies, and post-disaster recovery practices. Understanding them helps us prepare for the challenges and opportunities ahead. 1. Climate change impacts on high-density cities. Climate change intensifies many of the risks that dense cities already face. Higher temperatures, more frequent extreme weather events, and rising sea levels place significant pressure on infrastructure and populations. Key impacts include increased heat stress in compact areas with limited ventilation, heavier rainfall and urban flooding due to saturated drainage systems, coastal erosion and storm surges affecting waterfront districts, water and energy shortages during prolonged heat waves, greater pressure on public health systems in crowded neighborhoods. High-density cities must strengthen adaptation strategies, such as resilient infrastructure, cooling networks, and climate-sensitive planning, to cope with these accelerating challenges. 2. Urban heat islands and microclimate design. Dense cities often experience the urban heat island (UHI) effect, where built-up surfaces absorb and trap heat. This raises temperatures significantly compared to surrounding rural areas. To address this, microclimate design focuses on improving thermal comfort at the neighborhood and street scale. Effective measures include increasing tree canopy and shade, using reflective or permeable materials, expanding green roofs and green walls, designing wider streets with better airflow, introducing water features and evaporative cooling elements. Microclimate strategies not only reduce heat stress but also enhance livability, public health, and energy efficiency in high-density districts. 3. Resilient urban design innovations. Urban resilience is increasingly supported by innovative design strategies that integrate safety, flexibility, and long-term adaptability. Current innovations include modular and adaptive buildings that can be modified over time, multifunctional public spaces that serve both everyday use and emergency functions, blue-green infrastructure combining water management with ecological systems, resilient street networks designed with multiple evacuation routes, energy-efficient and low-carbon building technologies. These innovations aim to create urban environments that can withstand shocks, recover quickly, and continue functioning under changing conditions. 4. AI, machine learning, and real-time risk monitoring. Digital technologies are transforming how cities assess and manage risk. AI and machine learning enable the analysis of large and complex datasets, such as satellite imagery, sensor networks, mobility patterns, and climate forecasts. Applications include real-time flood or heat monitoring using sensor data, predictive modeling to estimate the impacts of earthquakes or storms, automatic detection of informal settlements or infrastructure degradation, early warning systems connected to mobile apps and public alerts, optimization of evacuation routes based on live mobility data. These technologies allow decision-makers to act quickly and accurately, improving the overall safety of dense urban areas. 5. Post-disaster urban regeneration and adaptive urbanism. After a disaster, cities face the challenge of rebuilding in a way that reduces future risk. This is known as post-disaster urban regeneration, and it emphasizes build back better principles. Adaptive urbanism goes a step further, encouraging cities to evolve continuously based on new knowledge, changing demographics, and environmental conditions. Key principles include rebuilding with stronger building codes, redesigning street networks to improve evacuation, restoring ecosystems and natural buffers, providing safer housing for displaced populations, engaging communities in planning and decision-making, promoting flexibility so the city can adapt to future uncertainties. Together, regeneration and adaptive urbanism enable cities not only to recover but also to emerge more resilient than before.